In the midst of a global pandemic, the US and other countries are implementing a variety of strategies designed to flatten the curve. How well are they working, and how can we tell? A recent paper published today in Science points out an unusual power law scaling of the rise of new cases in China. They extended a well-studied model and showed how these scaling laws are in some sense universal. Understanding and incorporating the effects of our response to the threat of coronavirus can be helpful in managing the crisis and in preparing for new challenges. You're watching 11 Levels. Note that this is not based on the series 5 Levels by Wired.com. Okay, maybe just a little bit. The study published today by Benjamin Meyer and Dirk Brockman focuses on a distinctive power law increase in confirmed cases. Here you can see the number of confirmed cases plotted versus time on a linear scale for mainland China in January and February of this year. There's a clear deviation from exponential growth, as you can see from the inset graphs that show power law behavior. Further analysis of these results in provinces in China show a distinct power law scaling as well, with a power law of around 2 to 3. The fact that exponential growth is not observed is highly surprising. Why is this power law behavior so surprising? Well, to understand this, we need to consider the SIR model, which is a minimal model of epidemics that is widely used to understand the spread of infections like coronavirus. I described this model in 2 previous Level 1 videos, and I will only summarize it here. In the SIR model, there are 3 populations: S for susceptible, I for infectious, R for recovered, people who are no longer infectious. The coupled set of equations yields a universal response curve like you see here. What is characteristic of this model is exponential rise in the number of infected population, not a power law. And yet, the data shows power law behavior. This is disturbing to a physicist like myself and to the authors. So to explain this behavior, they introduce a new phenomenological model that they call the SIR-X model. Let's take a look at this model. So the SIR-X model is obviously derived from the SIR model, but now there's a new population which they call X, which refers to the population of people who are social distancing or otherwise self-isolating. This number is not static and will be modeled like all other model populations. So here's the full set of definitions for these coefficients. R now stands for the removed population, while X stands for the quarantine population. There are 2 distinct rates for containment and quarantining. Both have some influence on the outcome. When the authors considered this model, they are able to fit the early time dynamics of the outbreak in China, which suggests that the power law is universal. I decided to play with the model myself. Since I had already created a mathematical model of the SIR model, it was a generalization to the SIR-X model was straightforward. Here you see a plot of the time evolution of the 4 populations SIR-X for a range of k parameters. The 3 graphs are showing the same results but in different ways. On the top you have a linear scale, in the middle you have the population plotted on a log scale, and on the bottom both population and time are plotted logarithmically. The log-log plot on the bottom shows a straight line for the X population, which eventually flattens out, just like the results coming from China. So there are a few more notes to highlight from the paper. One is that the main effect of power law is attributed to the exponentially increasing number of shielded population, which helps to mimic the herd immunity effects that we are trying to avoid since they would involve the deaths of a large number of people. So the power law behavior comes from pitting exponential against exponential. The exponential decrease in susceptible population helps to achieve this lower rate of overall infection. The paper also shows that behavioral changes are effective in containing epidemics in the early stages, but in ways that were not obvious. The authors claim that their still simple model can help guide containment strategies for COVID-19 as well as future outbreaks.